Okay, so now we want to talk about basic stoichiometry, and basic stoichiometry can be executed in a simple set of steps. The first step being to write the balanced chemical equation for the reaction. So we have to have this because this is our recipe that relates all of our different pieces together. The next thing we'll want to do is to write down our given quantity and convert that quantity to moles if it's not moles already. All reactions are written such that the coefficients can mean the number of atoms involved or the number of moles involved. We rarely work in atoms because the values for atoms are very hard to determine in a lab setting. So we generally work in moles because that's something we can work with. Next, we'll use the mole ratio from that balanced chemical equation so that we can convert the moles of the substance we have into the moles of a substance that we are looking for. So basically, we're using the fact of our recipe to do this. This would be like having a sandwich and knowing that it takes 2 pieces of bread to go with 1 piece of ham. If we had 5 pieces of ham, we could figure out how many pieces of bread we needed. It's the same general idea. Number 4, if we want that value for the material that we're looking for in some quantity other than moles, we need to go ahead and use another mole conversion to convert it back. This is because moles are not easily measured in the lab either. Typically we work in things like mass or volume of a gas or volume of a solution, and so sometimes we have to do this work to get where we need to be. And then number 5, we're going to ask ourselves rhetorically, does our answer make sense? And if not, we're going to work to correct the issues. All right, so here's an example of a basic stoichiometry problem. We want to find the mass of lithium metal that we can produce when we take 250 grams of lithium oxide and decompose it with heating. So the first thing we're going to do according to those steps of stoichiometry is to write a balanced chemical equation. Now this was covered a few units ago, and so your students should be able to do this. If not, they need to come see me and we'll work on this a little more together. So for this system, we have 2 Li2O moles, that's moles of lithium oxide, producing 4 moles of lithium metal and a mole of oxygen gas. So step number 2 then is to write down what I know. Well, I know that I have 250 grams of lithium oxide. I also need to convert it to moles, so I'm going to use the fact that 29.88 grams of lithium oxide is equal to 1 mole. I know that from the periodic table. I have 2 lithiums at 6.94 grams apiece and 1 oxygen at 16. That's 29.88. All right, step number 3 then is to convert the moles of what I have into the moles of what I want. Well, my goal is to get to lithium metal, so I need to trade lithium oxide moles for lithium metal moles. And so I do that by using the mole ratio. If you look in the balanced chemical equation, there are 4 moles of lithium involved for every 2 moles of lithium oxide. So what I'm trading goes on bottom so that it can be traded out, and what I want goes on top so that I can keep it. Now finally, it wants to know the mass of lithium metal, so I'm not quite done. I've got it in moles, but I can't really measure that in the lab. So one more little mole conversion. We're going to use the fact that 1 mole of lithium is worth 6.94 grams, again, from the periodic table. If we look up lithium, it says every lithium is 6.94 grams, and we end up with a total answer of 116 grams of lithium. Now, does this make sense? Well, yes, it makes sense because we have less lithium than the lithium oxide we started with. That's one thing. Number 2, if you look at the mass of a lithium oxide at 29.88 and the fact that lithium makes up about 14 of that, it's a little less than half. Well, our answer there at 116 is a little less than half of the 250 we started with. And so does it make sense? Yes, it does. And so we'll accept this answer and go on. The next idea we want to talk about is how to use stoichiometry in the context of a limited and excess reactant problem. Essentially, when we have this going on, the components are not mixed in perfect stoichiometric ratios. This is also more like real life. Things are generally not mixed perfectly every time. And so one reactant will be consumed and the other will not. So the steps are going to be pretty similar. The first thing we'll do is write a balanced chemical equation. We have to have that recipe for any stoich problem before we can solve it. Next, we need to use basic stoichiometry to convert the known amount of each reaction given to the product of interest. And so in this case, I'm just going to choose, if they want to know about, say, reactant, how reactant B relates to product A and how reactant A relates to product C, we're just going to pick one of them and go. And so you'll see that in the example problem. Whichever chemical species produces the smallest amount of the product we chose, that is the limiting reactant. And that amount that it produces is what is called a theoretical yield. That is how much, in theory, I should get from this reaction if everything goes according to plan. Now, things normally don't always go according to plan, and we'll deal with that later, but that is what that value is called, the maximum amount that can be made from the limiting reactant. Step number 4, or thought number 4, is to know that all the limiting reactant is used up, and that in the amount of it that was used is what determines the amount of all other species that we use or produce. So everything else from that point on is based on it. And the chemical species that has more than what's needed, we call that the excess reactant, and some of it will be remaining after the reaction is completed. That has to be true in order to satisfy the law of conservation of mass. All right, so how does this look in an example? Well, let's say a student wants to mix 25 grams of iron and 252 milliliters of a 0.325 molar aqueous solution of copper 2 nitrate. What mass of copper metal can be made, and how much excess reactant is left? So now we're dealing with molarity as one of our knowns. Molarity is a little different. If you'll take a look at the mole paper I sent home with your students, it'll give you a little more insight into that. But basically, this is where we take a given amount of a substance and dissolve it into water or some other solvent to make a solution that we can use. This is especially helpful when you're dealing with salts and other reactants that are water soluble. So step 1 in this process is still to have a balanced chemical equation. It takes 2 moles of iron to go with 3 moles of copper 2 nitrate to produce 3 moles of copper and 2 moles of iron 3 nitrate. Next thing we need to do is convert each of them to the product of interest. Well, according to this, we want to know how much copper metal can be made. So I'm going to say copper is my product of interest. And so I'm going to repeat steps 2 through 5 twice. For each reactant individually, I'll do it once for a total of 2 times. So we'll start with the 25 grams of iron. We write down what we know. We convert it to moles using the mass of iron from the periodic table, which is 55.85. Next, we use a mole ratio between iron and copper. According to the balanced chemical reaction, 3 coppers can produce 2 irons, or 3 coppers can come from 2 irons would be more appropriate. And since we want to know what mass of copper metal, we might as well take it all the way. Step 4, we'll convert out of moles using the fact that the periodic table says 63.55 grams of copper is worth 1 mole of copper. That gives me a value of 42.7 grams of copper possible if I used all the 25 grams of iron. Now, we also know about the copper 2 nitrate, and it might tell a different story. So we'll start with it at step number 2 as well. I have 252 milliliters of a solution that has 0.325 moles of copper 2 nitrate for every 1,000 milliliters, or 1 liter. That's what the little capital M means up there. Your student should know that, but if they don't, or you don't, now you do. Capital M stands for the number of moles in 1 liter, or the number of moles in 1,000 milliliters. Those are equivalent. And so now I just need to do my mole ratio, my step 3. According to this balanced chemical equation, 3 moles of copper can be made when 3 moles of copper 2 nitrate interact. Step 4 says that 63.55 grams of copper can be made for every mole of copper. And so this reaction using the copper 2 nitrate produces only 5.2 grams of copper. Now, only one of these can be true, and if you think about it, it makes pretty good sense which one it is. If I only have enough copper 2 nitrate to make 5.2 grams of copper, then I would never have enough copper 2 nitrate to react with all the iron to produce 42.7 grams of copper. It's just not possible. And so when you get to this point, the smallest value is the theoretical yield, and it comes from the limiting reactant. So in this case, copper 2 nitrate is the limiting reactant because it's the one that produces the lesser amount of product. And that 5.2 grams, we'll call it the theoretical yield. Now, the rest of this question wants to know how much excess reactant is left over. Well, the excess amount of copper that we predicted we could make is directly related by stoichiometry to the amount of excess we have left. So that extra 30-something grams of copper that the iron said it could make is related to how much extra iron there is. That's what we mean. So really all we have to do is find the amount of extra product that we predicted above the 5.2 grams that will actually be made, and then convert that directly to the desired quantity of excess reactant. In this case, we want to know mass of iron. So we want to take that amount of copper and change it using stoichiometry to the mass of iron. So how much extra copper was predicted? Well, the iron predicted 42.7 grams. We know in truth, based on the limiting reactant, copper 2 nitrate, I can only make 5.2 grams. That means I had enough extra iron to make 37.5 more grams of copper. It didn't happen, but I had enough to do it. And so that's enough. I can use stoichiometry to relate them. So this time I'm going to start with my 37.5 grams of fictional copper that could have been made. And I'm going to convert it to moles, because the first thing we always do in a stoich problem is convert to moles. So 1 mole of copper, we're 63.55 grams. Next thing I'm going to do is mole ratio. I want to swap copper for iron. Well, 2 irons can be made every time 3 moles of copper are involved. And last but not least, I want this in mass. So I'm going to take iron 55.8 grams for every mole and see how much mass that would be, and it would tell me I had about 22 grams of iron remaining. Does this make sense? Yes, it does. It makes sense because this is less than my original amount of iron, and it also represents a relatively small amount of iron used, which should make sense seeing as how we made a relatively small amount of product.